And now for something completely different. Or maybe not so, because it's about how new mathematics comes into being and how it is created by mathematicians, like the folks you've just heard. This is going to be first of an advertisement. There's a book called Where Mathematics Comes From, which has lots more stuff than I will be doing here. It's an easy-to-read 600-page book. Easy because it's written easily, but it goes all the way up through the cognitive foundations of lots and lots of mathematics, far beyond what's in this talk. Then there is a book near completion, Conceptual Science, the Neural Embodiment of Thought and Language, by myself and Srini Narayanan. What we're doing is trying to look at what kinds of neural circuitry would be needed to characterize human thought and language. We're just about done with what we have so far. And with lots of help from my friends, Rafael Nunez and Aaron Siegel and Srini Narayanan. And my wife, for all of the other patience required to go through all that. An earlier version was given as the Cafetz Lecture at the Fields Institute in Toronto, and Fields has got an international program in cognitive science of mathematics, the Fields Cognitive Science Network, which started from Where Mathematics Comes From. Now, I first got into the idea of looking at the human basis of mathematics in 1963 when Paul Cohen came out with his proof of the independence of the continuum hypothesis. And what Gödel and Cohen had done was to use different versions of Zermelo-Fraenkel set theory with the axiom of choice. With Gödel, of course, without forcing years before it was invented, and Cohen with forcing. And Gödel had proved with one model of the axioms of set theory that there's no level of infinity between Aleph null and 2 to the Aleph null in the Cantor continuum hypothesis. And Cohen comes along with forcing and shows the opposite, that if you have forcing, which is a different model of ZFC, you get different, lots and lots of levels of infinity between Aleph null and 2 to the Aleph null. And the idea is this. What Gödel showed is it can't be the case that ZFC is always false. Cohen showed it can't be the case that it's always true, and therefore it's independent. But what's interesting is that you get two different forms of arithmetic. And not only arithmetic, everything that's based on set theory, all forms of mathematics which use set theory, and it's hard to imagine one that doesn't. So you have here two mathematicians. They give rise to two different versions of mathematics, and that's a very interesting phenomenon. What that shows is that mathematics is not out there in the world by itself. They're both forms of mathematics. And not only that, since Cohen's work, you have lots and lots of other work based on forcing and other things, all the work on measurable cardinals and so on. So lots and lots of new mathematics of all sorts that is there, and it's not objectively out there in the world. You guys who are mathematicians are inventing it, as you've just seen in a magnificent talk or two. Now, that's the idea. Mathematics are people. And the question is, if mathematicians are creating mathematics, how do they do it? And there are three parts. One, ordinary neural mechanisms for thought, which Narayanan and I will be talking about in the book that's just about done. Ordinary human thought structures and processes, which have been studied in great detail in cognitive linguistics since about the mid-1970s. And then special constraints that make form of thoughts, quote, mathematical. So not every kind of thought is mathematics. There are certain things that are special about mathematics. In particular, mathematics is precise, consistent, inference-preserving, symbolizable, calculable, stable across time and communities, and effective for description, explanation, and prediction in many everyday activities. Not every form of thought is like that, right? That's what's special about the kind of thought used in mathematics. What's ordinary about mathematics is, first, you can do it, yes. It uses ordinary mechanisms of thought. So, for example, these were discovered in cognitive semantics over the last 40 years. Processing schemas, or what Narayan has called executing nets, image schemas, conceptual frames, following Chuck Fillmore, conceptual metaphor theory, conceptual integration, conceptual bindings, mental simulations, and symbols and symbolic links between symbols and their meanings, which are called constructions in construction grammar. So this is basic stuff in cognitive linguistics. I don't know, probably no cognitive linguists in the room, but if you happen to sit in on CogSci 101, you'd know all this. Now, sorry about that, but we were told to be sophisticated. Now, then there is another part. There are ordinary neural mechanisms that are used in this, and we can click in this. First, you need to know that ideas don't float in space. Very important. Ideas don't just float in space. They are all physical. They are constituted by systems of neural circuitry, both in the brain and in the neural connections to the body that allow bodily functioning in the real physical and social world. And it's easy to see that reasoning is not just in the brain. For example, if you were to take a look at all of those nice pictures of, connections in the brain, as if there were no gaps, as if there were just connections all over the brain, and if thought was just in the brain and it were not connected to the body, there would be nothing to think about. Think about it for a minute. If that was what thought was, there would be nothing to think about. What we started discovering in the 1970s is that thought is embodied in lots and lots of ways. And one of the things that has been discovered in fields like cognitive linguistics, like experimental embodied cognition, and so on, is the details of how that works. And there are lots of studies, books, et cetera, on this. If you want a great book on it, Ben Bergen's recent book on simulation theory is really great. That would be a good place. I can recommend that to you. Now, all meaningful thought functions in this way, including mathematical cognition, with the extra proviso of what makes it special. So the idea is you're going to be using mathematical ideas constituted by human brains, and that means that the nature of mathematics is a scientific matter for the cognitive and brain sciences. That's a big deal. It means mathematical foundations alone, if you deny the results of the cognitive and brain sciences, cannot characterize the nature of mathematical ideas. Think about it for a minute. If you ignore what's going on in the cognitive and brain sciences, if you're science deniers, and I mean the science of the cognitive and brain sciences, and some people in science are science deniers of this kind, then you can't just take mathematical foundations in logic and model theory and so on and say that's the foundations. And that's how human mathematics works, because mathematics is made up by human beings like you guys sitting in this room. So that's what this is about, and that's what that book is about. Now, there are neurally embodied primitives, and we know that there are things like image schemas, which have Gestalt structures with semantic roles. They include things like containment. This room is a container, right? The bottle sitting over there of water is that's a container. Coffee cups are containers. All sorts of things are containers. The Bounds of Berkeley is a container, okay? This building is a container. And containers in general have interiors, exteriors, boundaries, and contents, and sometimes portals that go in and out. Now, that is crucial in containment, and that is structuring what you see. The same thing is true with locations in space, with motion, where you have a source, a path, a line, and a thing that moves. Those both are topological structures. We can go into their topological structures, and we think they're done by topographic maps of the visual field. And then you have things like adjacency, contact, nearness, various orientations, directions, rotations, which we'll get to in later, center and periphery, deixis, very important, and viewpoint, and so on. Deixis is where you're located and what you see as a viewpoint. Also under image schemas, you get basic shapes, circles, ovals, triangles, rectangles, squares, arrays, which will be very important as we go along. And then there is subitizing, which you have with small numbers, like 1, 2, 3, 4. And these are computed by neural circuits which were worked out by Dehaene and company in Paris. And babies have them, and monkeys have them, and pigeons have them. Inferences, XNets, and neural bindings across semantic roles, we'll talk about XNets and those later on. Those are also neurally embodied primitives. Now, active S-spectral schemas are very, very important in all of that. What they do is characterize the structure of events and actions in the world. Now, in neural computation, this was discovered by Srini Narayanan back in '92. Srini was doing modeling, computational neural modeling with structured neural computation, not PDP. And what he showed was that if you model the motor system, which is hierarchical, which he did, and he took a model of the body with every bone and muscle and joint and so on, and showed how to make it move and do ordinary actions. He had to do the hierarchical modeling that you would have in neurophysiology. Then, if you look at the highest level, it generalizes across all actions and events as understood. He called these executing networks, or XNets, and they have very simple structures: preconditions, a start, central conditions that you do, a test to see if a goal has been met. Perhaps you're iterating something. If I want to take a drink, I have to iterate and take a drink. You finish, you put it down, and then there's a resulting state. What's interesting and important about this is that every single language in the world has in its semantics that structure. It's called aspect. In English, you get things like, I'm about to do something at the beginning, preconditions met, you've started doing something. If you're in the middle, you are doing the being, I am drinking, for example. If you're if you're doing an iteration loop, you get he drank and drank and drank. If you get finishing up, you say, I'm done. And if the resulting state, I have drunk some water. The have and past participle marks that. That's English. Every language can mark these things. What that means is that you are using the way that your body works in your motor system to understand all events and actions in the world. And then the logics of those events and actions, which were not able to be worked out by logicians, and I worked in the logic of natural language for about a dozen years before I got into this, they couldn't do that. It turns out to fall out from the programming of the system. The logic is a consequence. And that's very important. Just as you have the logic of containment as a consequence, because you have, if A is in B and B is in C, then A is in C. Very familiar. Now, I want to talk about conceptual metaphors, which are mappings from source frames to target frames. They're neural mappings in the brain, and we can talk a little bit later perhaps about how those work. But you have these neural mappings in these layers for neural circuitry. And we're going to go through lots of examples of this. But particularly, the most important examples in the basis of the system are primary metaphors. For example, more is up and less is down. Prices rise, they fall, they hit bottom. You can say turn up the stereo, turn down the music, etc. Now, that's a general primary metaphor, but you have lots of others. And the grounding of this, let's say this metaphor, comes about because quantity correlates with verticality in everyday experience. Every time you pour water into the glass, the level goes up. You pile more books, the level goes up. And repeated simultaneous activation in distinct brain regions, that verticality and quantity are not in the same regions of brain. What happens is when you repeat those, anything repeated for a circuit strengthens the circuit, and you get, since every neuron is connected to 10,000 others and you have groups going out along existing pathways, you get spreading activation. That activation spreads and it's strengthened along existing pathways till you see a common path from one region to the other that forms a symmetric circuit. And at this point, STDP takes over. STDP, spike time dependent plasticity, think about it like this. You've got a neuron with an axon, another neuron with an axon. You're going in different directions. They come together like that. The one that normally fires first is strengthened in its direction, and the other one is weakened all along the path. The result is that you get an asymmetric mapping. And we believe that this is the prediction of the source and target of primary metaphors and the entire metaphor system. We think we can predict what the source and target of conceptual metaphors are for the hundreds and hundreds of metaphors, and in fact the hundreds of primary metaphors, probably thousands of complex metaphors. So this is our guess for primary metaphors, and that's what we think does that. And what primary metaphors do, the things like purposes or destinations, or things you're trying to reach, right? We'll get lots of things like that. There are hundreds and hundreds and hundreds of these that have been found. Now, in arithmetic, there are basic grounding metaphors. Object collection, motion along a line, which steps are units, object construction, then the measuring stick, like you put your feet together or you measure things with other fixed objects. Now, what you have is a metaphor that arithmetic is object collection. What does this metaphor look like? Come on, there we go. In the source domain, you have collections of objects of the same size map onto numbers. The size of the collection is the size of the number. Bigger collections are greater numbers, smaller are less numbers. The smallest collection that's not empty is the unit, 1. Putting collections together is addition. Taking them smaller from larger ones is subtraction, which is why you add things to a container and you take them away. Have you ever thought of taking away? All right. Multiplication is, of course, iterated addition, and so on. By the way, that's just a small part of the mapping. In the book, Where Mathematics Comes From, the actual mapping takes 3 pages because there are a lot of consequences of that metaphor. So, but here are some of the entailments. First, closure. Adding and subtracting collections yields other collections. A plus B is B plus A. A plus B plus C is A plus B plus C, and so on. If you start looking at the properties of basic arithmetic, a lot of those, a vast number of them, 3 pages worth, show up as consequences of that metaphor. Similarly, arithmetic can be seen as motion along a line, where locations of a line are numbers. The origin is motion, that's called 0. A step in the forward direction adds 1. A step in the backward direction subtracts 1. A step backward from the origin, therefore, gives you addition of -1. Distances from the origin forward are positive numbers. Distances from the origin backwards are negative numbers. And then another few pages of inferences for that. The point is, those are how you basically understand arithmetic. And we all do, in terms of ordinary, everyday experience. Now, why is it that -1 times -1 is +1? Have you ever wondered why it is? Not only that it kind of works and so on. Ever wondered why it is? Why should that be? And there's a reason. It has to do with an experiment done by Roger Shepard and Metzler back in 1971 at Stanford. What they showed experimentally is that mental rotation is real and proceeds at a relatively fixed rate. So if you give somebody something like the letter A and the letter A rotated, and you flash it on very quickly and you say rotate this one till it fits that one, you check the number of seconds, you do this for different degrees, it turns out to be a straight line. It's not only a straight line for ordinary folks, but for those who are blind from birth and do it with Braille, it's the same result. It's not that you can physically see, it's what you see with your mind, what you do with mental imagery. And the idea is that these image schemas are structuring your mental imagery. Now, why is this the case? Suppose you imagine yourself on location on a path, your positive path forward. You perform a mental rotation of 180 degrees around the origin. Think of this from the side. And all of a sudden, you're at, instead of location M, you're at minus M. That gives you a metaphor of the form, a new metaphor. It says that rotation by 180 degrees is, guess what? Multiplication by minus 1.
Rotation clockwise or anti-clockwise?
What?
Rotation is clockwise or anti-clockwise?
Yeah, it's rotation around the origin, right? And it can also be shifting. All right. Now you do it twice. Do it again, and you get plus 1. Minus 1 times minus 1 is plus 1. Poof. Now, what you get a bonus of this, which is very interesting. That is, first of all, you can explain the cognitive minus 1 times minus 1 is plus 1 in terms of the cognitive reality of mental rotation. But there's a nice bonus. Imaginary numbers on the plane, in that imaginary plane, if you take, first of all, why is the axis 90 degrees from the real number axis? Have you ever worried about that? I worried about it from high school on. Why should it be 90 degrees away? Then you have another puzzle. Why is multiplication by I a 90-degree rotation anywhere in the imaginary plane? Right? Why? Because, very simple. You take the square root of minus 1 times the square root of minus 1, and you're going to get minus 1, which is a 180-degree rotation. So in short, rotation and imaginary numbers are tied together by this metaphor. That's it. Two of them is multiplication by minus 1. You have a consistent metaphorical system, which is kind of cool. Now, then there's infinity. Rafael Nunez, who's a cognitive scientist who studied the understanding of infinity by children in cognitive science, came to me and said, hey, how do we understand infinity in math? Because after all, we have no experience directly with infinity. It's got to be via metaphor. He said, well, I don't know how we do it, but we worked on it for a while. It was cool. And we came up with how we understand it. And the problem that Raphael posed was a particularly important problem. He said, how is it possible that infinity can be a single thing? How do you get infinity as a thing, like an infinite decimal, pi? Pi is a thing. It's an infinite decimal, but it's a thing. How do you get the set of all natural numbers? That set is a thing. It's infinite, but it's a thing. How in projective geometry do you get a point at infinity? And then you go to every other point, you get a circle at infinity. How do you do that? And it's a thing, but it's at infinity. What does at infinity mean? You have an infinite intersection on the line of successively embedded line segments. At infinity, it becomes a point. That's another example of what a point is. Now, this is a very important thing to understand. How is it possible for infinity to be a thing? Come on, you can do it. There. And the answer comes from aspect and from what we saw before of X schemas and X nets. This is how that works. Every language in the world has stuff like this in aspect, in the structure of actions and events. And one of the interesting things is that Narayanan showed that the neural mechanisms for this come out of motor control, the highest level of motor control, and then he created neural computational models to show how this works. And his neural computational model is a model for the basic metaphor of infinity as a thing. So here's how that works. First, let's go back to aspect. Languages distinguishes between an imperfective action, one that doesn't have an endpoint. He's walking. He's breathing. It's snowing out. The earth is warming, etc. A perfective action is one that has an endpoint. Instead of just he's walking, he walked a mile, endpoint. Okay? Now, so you have perfectives, and different languages can mark perfectives and imperfectives in different ways. Very common to mark them on the verb. Now, in general, they also have iterations, which are imperfective. The train rolled on and on and on. That's open-ended. But it's perfective with an endpoint. The train rolled on and on and on till Vancouver. That's the endpoint. Now, the way you understand infinity as a thing is using a simple metaphor. That infinity that goes on and on and on is imperfective. It's still going. Nothing's ended. Infinity that is a thing is perfective. How do you get it? The basic metaphor for infinity, namely, you have a target frame, the imperfective, the subject matter you're trying to understand, and the source frame, the perfective with an endpoint. The conceptual metaphor maps the perfective source frame onto the imperfective target frame by adding an endpoint in the following way. Here's the source frame, a completed iterative process. Here's the target, iterative processes that go on and on and on, right? That's on and on, infinity. The beginning state maps to the beginning state. The state resulting from the initial state maps to the state resulting from the initial stage. The process maps to the process. The intermediate result after each iteration maps to the intermediate result after each iteration in the process. Then, the final resultant state maps onto a thing that isn't there. It's a metaphorical addition. The final resultant state gives you an actual infinity, and there's an entailment. And the entailment is the final resultant state is unique and follows every non-final state. Similarly here, the final resultant state, infinity as a thing, is unique and follows from every non-final state. So,
We should wind up fair.
we're about to do it. We have a little bit more, about another 5 minutes. So now, we have cool things happening. Other mathematical metaphors. Numbers are sets. We understand numbers as sets. 0 is the empty set, etc. Then we can get, of course, get the set of all integers. This is not working. There we go. Spaces can be understood as sets. Points are members of those sets. Come on. Where does this go to? Here we go. Real numbers are infinite decimals. Real numbers can be seen also as infinite intersections and segments of the number line. We have 8 new different metaphors for real numbers in the book. Points in an n-dimensional space are n tuples of real numbers. And then you have Cantor's same-size metaphor. Now this is a big deal, and I want to come back to that. When Cantor says that for infinite sets, which we do not have experience with, for finite sets there's a one-to-one correspondence, gives you same size. But he wants to say the same thing works with a one-to-one correspondence for infinite things, and then he takes that as literally true, not as metaphoric, but as literally true. And when he does that, you get something very weird in that. You get the idea, we're going to get to this next, that, there's the same size, there's just as many integers as there are even numbers. And you say, wait a minute, what about all those odd numbers? And the answer to that is, well, what he's really talking about is there is a one-to-one correspondence, not that they're really what we understand as the same size, because the notion same size that we intuitively have is not there in our experience for infinity. But that's fine. That's a great metaphor that was taken as literal in mathematics. Now, what's interesting about Russell's paradox is that you get things like this sentence is false. Come on, you can do it. If it's true, it's false. If it's false, it's true, etc. You're familiar with that. Now, right? Now, what's interesting is that when Gödel took that, he took it as improvable. If the sentence is provable, then it's, if it's not provable, then it is, and if it's not it's provable, then it's not. And what he did was use a technique of Cantor's. Now, the thing about this sentence is false, is it's not about anything in the external world. It's only true of itself. It has nothing to do with anything external in the world. And that's going to be very important as we go on. What Gödel did was this. He took this, he said, we can say this sentence is unprovable, and he set up a way to show it would be provable if proved unprovable, etc. And what he did was he used Cantor's diagonalization as a method key to such a proof, and here's Cantor's metaphors and the diagonalization. So Cantor's metaphors are same size metaphor, two sets of the same size of thing put into one-to-one mapping, etc. Now, what's interesting is these can be formed by the basic metaphor of infinity. And all infinite sets of natural numbers are of the same size as the infinite set of all even integers in this. Okay, now, given this, what Cantor did was form an array. And he took the following idea. He said, suppose that, let's assume that there were just as many infinite decimals as there are integers, and suppose that we just take a line, we do this, axiom of choice, we choose one, we go like that. And then what we do is we take the diagonal, like this, and we do an operation on this array. This array is an image schema. It's a complex image schema with numbers. And we perform an operation, and the operations are performed how? Using XNets, okay, X schemas. So we do that, and what we do is we do substitution infinitely. We have, again, the basic metaphor of infinity applying to an operation. The operation says you take a number here. If it's not 9, you make it 9. If it is 9, you make it 1, all the way down, and you do this operation according to the basic metaphor infinity all the way out, right? And the result is you now have to interpret what happens. And the interpretation is what's interesting. The interpretation says something wild. It says that there are more, according to Cantor's metaphor, in real numbers than there are integers. And that means, since they're both infinite, there's a bigger level of infinity. Okay? That's why, and he said that is the idea of Aleph null for integers, 2 to the Aleph null for the real numbers. So that's what he did, etc., and we go through there. Now, I want to stop here and talk about the future, but I want to point out one thing. These slides are going to be available to you, but with a second half. And that's second half adds 3 more metaphors of Gödel's, Gödelization metaphors. And when you add those to this, you get Gödel's incompleteness theorem, a version of it. And it's straightforward, and you'll be able to see it, and it's easy to follow. Now, the future directions are cool. First, new forms of higher math are formed via conceptual integrations of 2 prior forms of math by conceptual metaphor or analogy, as you have just seen. And the question is, what exactly are those metaphors and analogy, and what do they look like from the perspective of cognition, of cognitive semantics? And what do they look like neurally from the neural modeling of that? Then you have the issue was brought up of the Langlands program of Wiles's proof, which is, again, presumably a lot of analogies of the sort that you just saw in the previous talk. But now the thing that I would like to see understood really well is the following. What cognitive and neural mechanisms are required to interpret a formal proof? I just gave you this thing of this array. How did you understand it? I described it in English. What was the cognitive operations you used? Was it frame semantics? Were there metaphors? Exactly what were the cognitive operations? Because we can now specify those precisely. What role will frame semantics play? Because that's got to be there, as you can see. Will a mapping from a frame to a proof suffice? What kind of examples would be convincing? And the converse, which is, how do you take an idea that you have about mathematics and formalize it? What is the actual cognitive mechanism for doing that? And the idea is, and you want an interpretation of Gödel, the following slides will be, you can look at that. But this is wild. Mathematicians and or other folks do this all the time. How do we do it? We know a lot about the details of conceptual structure in terms of frames, metaphors, etc. How do they work? And we know a lot about their neural structure. How do they work? That, I think, is a cool future direction. Thank you.